class.
So we're happy to have Ben Gammage from Harvard, who will tell us about Abelian 3D mirror symmetry.
Okay, thanks again for inviting me to speak. Very fun to be here. As I was just telling Eva, now that I realize it's so easy to come down here, I'll have to come more often. Anyway, so I'd like to issue an apology at the beginning that there's going to be some non-trivial amounts of physics in this talk, which I think if there's unavoidable physics in a mathematics talk, usually that means there's something the speaker doesn't understand. Which is certainly true. But anyway, I've distilled the main mathematical content of this talk right here, in case anyone zones out on the physics, which is that the functor from filtered vector spaces to graded vector spaces, which takes a filtered vector space to its associated graded, is the universal spherical functor in a certain sense. So I'm going to define spherical functors later on in this talk, and I'll also explain in what sense this is a universal object in that context. But that's what the mathematics of this talk is going to be about. Oh yeah, and I certainly encourage people to interrupt me because I may be sort of, I take a perspective on, ultimately I hope to connect to things that are very familiar to geometric representation theorists, causal duality, category O, and so forth, but that might not happen until the very end of my talk. And in the meantime, I might take a perspective that's very different than what's usual. So I encourage people to jump in and ask questions. So let me start with part 0. Which is a little warm up. And so I mentioned that this talk from the title, we see it's about 3D mirror symmetry. So that's something that I think, a phrase that people in the audience of this talk have heard a lot. Let me warm it up by reminding you what 2D mirror symmetry is, which is a little more familiar to mathematicians. So 2D homological mirror symmetry. This is, of course, in the formulation I'm saying, this is due to Convolution. And what the statement of 2D mirror symmetry is that to a Kähler manifold X, associate a pair of categories which I will suggestively call A2 of X and B2 of X. So this A2 of X is the Fukaya category of X. I know that this is something that is not very familiar to a lot of the audience of this talk. So let me just say that something like, you should think of this as being something like, something like under a Riemann-Hilbert correspondence, something like a deformation quantization of X, a holonomic modules over a deformation quantization of X. This is in fact the subject of some current work by Maxime Frantsevich and Jan Soidelman and several other people. But if X equals T star M, if X is the cotangent bundle of some variety, then you should imagine that the category of X is some category of perverse sheaves on X, maybe with some Lagrangian singular support condition. Sorry, on M. So, and for instance, if L is just the 0 section, this is just the category of local systems on M, right? Perverse sheaves on M with 0 singular support. Okay. This category B2 of X is the category of coherent sheaves on X. So those are a couple of categories which are pretty familiar. So I'm not done with this statement. So the statement of 2D mirror symmetry says that you know, these Kähler manifolds often come in dual pairs, and X may have a dual space, mirror space X check, such that the one category assigned to X agrees with the other one assigned to X check. So that's the statement of 2D mirror symmetry. And now let me give this, let me give an example. The one example I really care about in this context, which is the example where X is C star, and it turns out in this space the dual space is also C star. So this goes by the name of the Fourier transform. And why do I call it the Fourier transform? Well, this C star is T star S1. So I see that my A category, oops, I call it A2 of X, the 2 stands for 2D mirror symmetry. I'm not explaining what that means. This A2 of C star is the category of local systems on S1. And this is, of course, modules over the category of the group ring of S1, right? That's what it means to be a local system on S1. It's a representation of the fundamental group of S1, or modules over the group ring of that thing. And this is the group ring of the fundamental group of S1 is equal to functions on the dual copy of C star. And this thing is equal to coherent sheaves on C star, which is this B side category associated to X check. So I can pause for a second so everyone can check that I've done this right. If I were more careful, I would have called this one, say, T and this T check, say, to indicate that these were dual tori here. And so what I'm saying is that this homological mirror symmetry, 2D mirror symmetry in this case, gives a spectral decomposition. Homological mirror symmetry gives a spectral decomposition of local systems on S1. Right, we have this kind of what someone involved in geometric representation theory might call an automorphic category, and we're relating it to some spectral category. So given any local system on S1, we can sort of, the points of this dual space correspond to the eigenvalues of the monotropic operator. So this is just the Fourier transform. It should be pretty familiar. But let me pause if there are any questions. Okay. And let me one little.
We do have.
Hey, Ben. Hey, I could save this question to the end, or you could say the answer to the end. Is there a 1D? I guess I'm confused about. I thought this was just mirror symmetry, but you're calling it 2D mirror symmetry.
Yes. Mirror symmetry is an equivalence of. So yeah, I can say this out loud. I'll say it a little more later. I don't want to get too into physics in this talk, but mirror symmetry is an equivalence of 2D field theories. And a 2-dimensional topological field theory is something that, to a point, assigns you a category. So this is an equivalence of a pair of categories. So these categories, you should imagine, are what my 2-dimensional topological field theory assigns to a point.
Is there some sort of 1D mirror symmetry that I should also have in mind?
Category, well, no. The answer is no. No, because it has to do, again, I don't want to get too into this.
Okay.
You can ask me after the talk, but 2D mirror symmetry and 3D mirror symmetry have to do with an involution on the sort of 2D and 3D supersymmetry of the algebras, which is somewhat special to those supersymmetry algebras.
Okay, so there is a family of supersymmetry algebras, but not necessarily a family of symmetries of them. Is that the sort of?
I'll just say this out loud. I don't know if this will be helpful to you if I'm just saying it out loud, but a Kähler manifold, maybe I'll write it down here. There's a 2D field theory, and it's a theory of maps from a Riemann surface to my target Kähler manifold X. So the fields in my 2-dimensional theory are some maps to X. And a 2-dimensional quantum field theory of maps to X, if X is Kähler, has what's called n equals 2, 2 supersymmetry. This has to do, these are like copies of the spin representation involved in the supersymmetry algebra, and there's some involution on this algebra which exchanges these two copies of the spin representation, which correspond to sort of topological twists, which take you to the A twist or the B twist. sorry, that probably was not that helpful.
I think it was helpful. Yeah, thanks.
Okay, okay. So the thing to keep in mind is this is an equivalence of a pair of categories because I was studying two-dimensional field theories. I'm about to study three-dimensional field theory, so I'm about to give you an equivalence of two categories. Sorry, an equivalence of a pair of two categories. I know. So, yeah.
Wait, a pair of
two categories.
okay, two hyphen categories.
Yes. Sorry, I don't know.
Two
how to say
categories.
it. Two
Yeah,
categories.
wonderful.
Well, yeah, you know, not well, a pair of
yeah.
two categories. Sorry.
Fantastic.
So, and let me just say, okay, yeah, Matt just asked if there was a pair of, if there was a 1D mirror symmetry. There's no 1D mirror symmetry, but there is a sort of 1D version of this Fourier transform, which exists in any dimension, right? Which instead of a pair of categories, there's a version of the Fourier transform. Well, maybe I don't want to get into this. Well, I mean, okay, we all know the classical Fourier transform, but actually, I'd like to give a 3D version of the Fourier transform, which might be involved later. Let me just state this as a lemma. No, actually, sorry. Let me give the 3D mirror symmetry statement. So let me say what 3D mirror symmetry is. Sorry, I should have done this. Okay, so that was the warm up. And now what's 3D mirror symmetry? I'll do this in a different color. 3D mirror symmetry is to a hyperkähler manifold, or really maybe a hyperkähler stack. We can associate two categories. So this means like something it has objects, and the Hom space between two objects is itself a category. And I'm going to call these categories A3 and B3, and these are going to be something else. Question mark. So let me. Do I want to say what these categories are? The problem is that we don't have a great notion of what these categories are in general, but we do in some special cases. And so, oh yeah, and then 3D mirror symmetry, sorry, is going to be the statement that X may have a dual hyperkähler stack X check, such that A3 of X is equal to B3 of X check. So the example I'm going to give is a categorified Fourier transform. So this is in the form that I'm discussing it. It's going to be in Telemann's ICM address, which is, so this is a categorified Fourier transform. Categorified Fourier transform. And in this case, my spaces X is going to be the cotangent bundle of C star, and X check will be the cotangent bundle of the dual C star. It's not necessarily going to be meaningful why these two categories are associated to these spaces, but we can go with it. Let me just write down what my pair of two categories is, and let's see if we can figure out why they're equivalents. So the first two category I'm going to write down is the two category of local systems of categories on the torus.
Someone in chat says they think you mean BC star instead of C star.
Thank you. Thank you. Thanks. Great. So, cotangent bundle of point clones. So this thing is of course an Artin stack, but it's going to be okay. So this is going to be the two category of local systems of categories on C star. So what do I mean by that? What I mean by this is going to be the two category of category C together with an action of the base loop space. Let me just call these. Let me just call these T and T check so I can be clear about my duality. So T is a copy of C star. So category C together with an action of the base loop space of the torus on C. And just like here, kind of, if I think about what this pi1 of S1 is, this pi1 of S1 was supposed to be telling me chains. This was chains on the base loop space of S1. So this was the base loop space of S1 is the thing that was acting. So likewise, I'm again just looking at modules for the base loop space of S1. You could even write chains if you want to linearize everything. I'm again just looking at modules for chains on the base loop space of S1, but now I'm looking at modules in categories. If I think about what this is, then this is the same thing as categories with an action of, what is the base loop space of a torus? It's the co-character lattice of the torus, which is the character lattice of the dual torus. Acting on C. So this is just a Fourier transform. Characters of the torus is the same as co-characters of a torus is the same as characters of a dual torus. And what's this? What's this? This is the same thing as categories C, which are modules for the monoidal category of quasi-coherent sheaves on the dual torus equipped with its convolution product. So I'll underline mod to note these are categorical modules. So this is a monoidal category. Convolution product. The convolution product comes from comes from the multiplication on the torus, and in turn, this is the same thing as modules for the category of quasi-coherent sheaves on BT check. So yeah, I haven't been careful about. I'm not going to be careful in this talk about coherent versus quasi-coherent, but the point of this statement is going to be that B3 events, the sort of spectral decomposition for local systems of categories on C star, is going to be coherent sheaves on coherent sheaves of categories is going to be, I'll write it this way, modules for coherent sheaves on BC star. This is a monoidal category, and I can write it like this. Sorry, this is a monoidal category, and I can produce a two category of modules for this monoidal category. So, okay, now I'm worried that everyone has got really bogged down in this example, which maybe means I didn't do a good job of presenting it. But the important thing is that somehow what I've done here is I'm saying that kind of I've given a spectral decomposition of local systems of categories on C star, which looks very much like this one, only I'm kind of one category level up now, and instead of my dual having to do with C star, it has to do with BC star. Which, by the way, that's why I mentioned the sort of one-dimensional Fourier transform. The usual Fourier transform in math relates functions on S1 to functions on the base loop space of the dual S1. So kind of in 1D, you have the base loop space of S1. Here you have C star. Here you have BC star. So you can kind of see where this pattern is going.
Ben?
Yes.
Can I interrupt? So being a module over, okay, so the 2D version of this on the A side, you had modules over pi1 of Z, or you had modules over the group algebra of Z. So this was like vector spaces with an invertible endomorphism.
Yes.
And so the categorified version would just be categories with an invertible endofunctor?
It's categories. It's categories with a map from. Is that right? That may be right.
So the left-hand side is just like categories with an invertible endofunctor. And you're describing,
It's, I mean, no, it's, sorry. So this thing acts, when I say this thing acts on C, what I really mean is that this thing maps to the Hochschild cohomology of C, right? So the Hochschild cohomology of C is endomorphisms of the identity in C. So this is
Okay.
a category C where sort of every object has an invertible, has an automorphism. Okay.
Okay,
So
cool.
yeah.
I have to say, this question. So, is there a version of this example where the cotangent bundle T is replaced with universal symmetry?
That's current research of us, and I can say that. Let me come back to that example in the question period. But my answer is that yes, I know it for SL2, and I know what the statement is supposed to be in general. Telemann told us what the statement is supposed to be in general. I only know the proof for SL2. But I'll come back to that question period if I can. So let me just add, so Justin requested that I add that this pattern continues. So I've done the 1D Fourier transform I mentioned. Here's 2D, here's 3D, and here's a lemma which in the precise form that I'd like to state, it hasn't appeared in the literature, so I'll attribute it to us, I guess. But it's you might call this the Betty Langlands equivalence, Betty geometric Langlands. When G is a torus. And what's this statement? It's a statement which you might call also the 4D Fourier transform. Right, geometric Langlands is an equivalence of four-dimensional field theories in the best formulation. And what's that going to be? It's going to tell you that local systems of two categories on a torus is going to be equivalent to, well, you can probably guess what the pattern is here. It's going to be equivalent to modules over coherent sheaves on B2 of the dual torus. So this gives you a spectral decomposition of local systems of two categories. So this is very nice, and the reason I stated this is I might need it later in the talk if I get to some material that I'd like to. But okay, we'd like to move beyond just the Fourier transform. Well, I don't know. Some of us, you can spend your whole life just contemplating the Fourier transform. It's pretty good. But let's get to the actual subject of this talk, which is we'd like to add matter. Oh yeah, and I should say that to a physicist, what I'm calling categorified Fourier transform, the 3D Fourier transform, they would call that particle vortex duality, because you have well, kind of you have a gauge particle on the x check side, and on the x side you have a vortex, right? You have something that has like winding modes along that torus. So that's a way cooler name for it, but we got to work on it. So what's this talk going to be about? In this talk, oh yeah, let me write out an exact sequence first. The usual hypertoric exact sequence. So I have C star to the n, and I have a subtorus T, and the quotient torus I'm going to call G. So in this talk, we're going to be considering the case when X is a hypertoric stack. So X is the cotangent bundle of C to the n modulo this torus T. And in this case, X check is going to turn out to be the Gale dual thing, which is the cotangent bundle of the dual copy of C to the n modulo the dual torus of G. So okay, that's what's going to happen in this talk. So that was all part 0. So now we're to the main body of the talk. So there's only 2 parts to this talk, I guess. Well, there might be a part 2. But here's part 1, which is spherical functors.
Can I ask a really naive question?
Absolutely.
Can you do kind of similar to this example for maybe other affine toric varieties, or do you have to use the full torus?
Affine toric.
Sorry, just like so, like maybe a sub variety of a torus. Okay, so here we've got we have a quotient, I guess, but
I mean, it's stuff,
Or maybe a more general toric variety instead of just like a nice torus.
oh, you mean the cotangent bundle, like.
Oh, yeah. Sorry, replace T with a toric, more general toric variety.
Good, so I'll deduce that at the end of my, so let me say, at the end of my talk, I'm going to possibly deduce something for hypertoric varieties, which a hypertoric variety is like, basically cotangent bundle of Pn is an example of a hypertoric variety.
Okay.
And sort of, the problem is that the general, a toric variety doesn't have a complete hyperkähler metric, but sort of if you can complete it by adding some stuff, and then you get a hypertoric variety.
Excellent.
So you can get a statement there, but it'll naturally follow from thinking about these, because hypertoric varieties are like quotients of this form, basically, when you throw out unstable locus in this,
Yeah.
in this quotient.
Excellent. Okay.
So for most of the remainder of this talk, let's stick to the case. So for now, let's just take the case when x is equal to t star c. So and in that case, I'm taking my torus t, I'm taking n to be 1 and my torus t to be trivial. So that means that x check is going to be the cotangent bundle of the dual copy of c mod c star. So now we come to this main question, which is, I can restate my main theorem, which I've unfortunately erased, but the main theorem of this talk, in sort of these vague terms, is that A3 of x is equal to B3 of x check, and vice versa. So now I have to tell you what these two categories are. This is an equivalence of two categories, where I'm providing some spectral decomposition of some two categories associated with this thing. And now I have to admit that I've really lied in my notation, because these two categories don't depend on, I hinted at this over here, I hinted at this somewhere where I've erased, that these two categories don't just depend on one of these holomorphic symplectic varieties, they actually depend on a choice of Lagrangian inside this variety. So actually what's going to be the case is I'm going to specify some Lagrangians. Let me call Lx is going to be the zero section disjoint union, or not disjoint union, I know whatever union, the conormal to 0 inside of T star C. So here's the 0 section and here's the conormal to 0. So this is a Lagrangian. And so really my two categories are going to be associated to these Lagrangians. So let me denote this like this. Let me call this Lx and A3 of B3 of Lx check. This notation is all kind of made up anyway, so I can feel free to say this. And Lx check is going to be the same thing, but mod C star. So Lx check is, C mod C star union the cotangent, the conormal bundle to 0 mod C star inside C mod C star. So in other words, it's this whole thing mod C star. So okay, so now I have to tell you what these two categories are. So question, yes.
I guess Lagrangian written down is not smooth, right?
No, it's not. As you can see, it's two smooth components, but they intersect at this point.
Then what does Lagrangian mean outside of the smooth case?
There's a good literature on this subject in recent years in the symplectic. Basically, the smooth points are Lagrangian. Okay. Let me just put it that way. Yeah. It should have, obviously, like it should have a stratification by isotropics and kind of the smooth open locus is Lagrangian. But I'm thinking of this as like a singular support condition. In fact, that's what I'm about to say. I'm about to just think about like what are perverse sheaves with this singular support. So that's something that should be very familiar to us as representation physics. So that's what I'm going to say. So what are these two categories? So these are a pair of two hyphen categories, and I would like to know what they are. And let's start with the A-side category, because that's kind of one of the main points of this talk is realizing what this A-side category is. And let me say, by the way, that kind of one of the big ideas of this talk is that a lot of what's happened in the 3D mirror symmetry literature in recent years, people sort of producing equivalences of categories or even of numbers or generating functions or something, is kind of downstream of the equivalence of two categories, which sees kind of more deeply into these topological field theories. Just like in mirror symmetry, if you're familiar with the prehistory of homological mirror symmetry, it started with like equalities of numbers in the 1990s, and only later did Conceived produce equivalence of categories. So this sort of now we're sort of finally trying to figure out what are these two categories. So let's before we do A3 of X, let's compute what this, before we do A3 of X with this Lagrangian, let's try and remember what A2 of X with this Lagrangian is. So as I said, A2 of X is like a Fukaya category or a category in a cotangent bundle setting. It's a category of perverse sheaves with this singular support condition. So this is a category of perverse sheaves on C with singular support given by the 0 section union the conormal to 0. So in other words, it's perverse sheaves on C stratified by a point and the rest of C. And so this is one of our favorite categories. It's my favorite category anyway. This is the category of a pair of vector spaces of like nearby cycles and vanishing cycles. And there's these maps X and Y. And there's these two vector spaces have monodromy isomorphisms on them, which I will call M psi. Okay, let me just call these whatever. M psi and M phi. And there's the relation that if I do xy minus 1, that's equal to M psi, M phi. And if I do yx minus 1, that's equal to M psi. So perverse sheaves on C has some quiver description. It's this quiver of two vector spaces, a pair of arrows between them, and the rule that if I do one arrow and then another, and I subtract 1, then the result is invertible. Okay, so how do we categorify this? Kapranov and Shefman, so if we want to two categories, we want to kind of categorify this description somehow. Kapranov and Shefman tell us how to categorify it. So categorify this via what they call perverse Schober's. So far, what I've written on the board, perverse Schober's is just like the name of, Schober is just kind of the German word for a sheaf of categories, I understand. So kind of a perverse Schober is like, whatever is the appropriate name for the categorification of perverse sheaves. What is it in this case? That basically there's almost no cases where we know what these perverse Schobers are, but one of the cases where we do know is in precisely this situation of C stratified by a point and the rest of it. So the category of perverse Schobers stratified by a point stratified by this Lagrangian LC, whatever, LX, is equal to SPH. So I'm going to call this SPH. This is the two category of spherical functors. Technically, nowhere in the literature is there a definition of a two category of perverse Schobers, so we can take this as a definition. So now I have to tell you what a spherical functor is. So, actually, sorry, I like to call them spherical adjunctions. So this is the two category of spherical adjunctions. So what is this two category of spherical adjunctions? What's an object of this two category? It's the data of a pair of categories, C and D, a pair of adjoint functors between them. So I have a functor F from C to D, and I have its right adjoint R. And then I impose the further restriction that TC and TD are invertible, are automorphisms. So what are TC and TD? I'm going to define TC is going to be the, hopefully I don't get this backwards. You can correct me if I do. TC is going to be the cone on the unit map of the adjunction. Unit map. And TD is going to be the cone on the co-unit map of the adjunction. Okay, so hopefully this looks, from what I've told you so far, like a very plausible categorification of this. What does taking the cone mean? For those of you who are sort of well-versed in categorification, taking the cone means like doing a subtraction. So kind of what this says is I have these two endofunctors on C. I have these two endofunctors on C, and I'm taking the cone on them, so that gives me a new endofunctor on C. And this is CP is an endofunctor on here, and I'm telling you that kind of if I subtract 1 from FRF, then the resulting thing I want to require to be invertible. So that's exactly what I did up here. So kind of this is, I don't know, if you, there's in this beautiful series of works by Kafarnov and Shefman, and now there's some additional work with Sogelman and Dickerhoff, and there's other papers of the kind of in this same vein that where kind of you meditate long and hard on linear algebraic descriptions of perverse sheaves, and then you think about what it would mean to categorify them. And so in this case, you have this beautiful answer. So this is the 2 category which I'm going to associate to the cotangent bundle of C with this Lagrangian singular support condition.
Can I ask one question?
Yes.
Oh, sorry. Hi, Ben. So question is like in previous case, you don't have any symmetry between X and Y. There's no way to tell which one's a left, which one's a right adjoint. Why in the categorical version, F is like
good answer. So you're saying that here I have F and FR, and it looks like I've broken symmetry here, that one of these is a left adjoint and one of these is a right adjoint. But in this case, X and Y were totally symmetrical.
right,
And
exactly.
the answer is that actually, so in this case, what's the symmetry of X and Y? There's a symmetry of this perverse sheaf category called the Fourier transform, right? And the Fourier transform entails like, if I look at this Lagrangian inside a cotangent bundle of C, and I could also have thought about it as cotangent bundle of the dual copy of C if I turn my head 90 degrees, and kind of that would kind of give me an involution of this category that entails switching psi and phi. And there's also a Fourier transform on this 2 category, where once again, I turn my head 90 degrees, and now I switch E and C, and I pass to left adjoints everywhere. So F gets replaced with FL, and FR gets replaced with F. And it turns out that the spherical functor condition precisely like guarantees that kind of that thing is still spherical, and kind of you've changed things by a twist. Somehow it precisely agrees with what happened up here in terms of like, I don't want to write down all the relations now, but that's my answer is that this spherical functors have a huge amount of symmetry, which I haven't shown you so far. Does that kind of answer the question?
Okay, start off. Thanks.
Sure. Yeah, so this spherical functor category, unfortunately, I'm not going to have enough time to go into all of its miraculous properties. Spherical functors are really incredible, though. They show up all over the place. I hopefully will go into some of them. They're especially ubiquitous in kind of mirror symmetry. Well, yeah, maybe I should, as long as I'm here, just say a couple words about spherical functors. But let me just say, so the goal of this talk is to, I mean, the main theorem which I've stated there is a spectral decomposition of spherical functors. It's a way of writing this 2 category as some kind of algebraic 2 category. So that's to my mind a very noble goal. So I'll just maybe very quickly say a couple of examples of spherical functors. So if X is a smooth variety, and then D is a smooth divisor, then the push forward from coherent sheaves on D to coherent sheaves on X is a spherical function. It's spherical. And similarly, well, yeah, let me just leave it at that. There's a sort of mirror example which we see often in Fukaya categories, where a Fukaya sidal category mapping to its boundary, and that matches precisely with this. But so spherical functors occur, very often, as we can see from this example. Any other questions? Okay. So now I need to tell you what my B side is, so that I can figure out what's the mirror to spherical functors. And you might have guessed from the example I told you before what the B side is, although you'd be slightly wrong because of my non-smooth Lagrangian, because my Lagrangian has multiple components. So in this case, my B3 of this LX check, which you remember this sits inside of a cotangent bundle of C mod C star, this is going to be coherent sheaves of categories on C mod C star. So just like, oh no, I just erased it. But just like in the other case, when I told you that when my X check was the cotangent bundle of C star, then the answer was kind of modules over, or sorry, if I told you the cotangent bundle was BC star, then I told you I was looking at modules over coherent sheaves on BC star. So here's something similar, except that I want to require with singular support contained inside of L, inside of this LX check. So unfortunately, this notion doesn't have a definition currently in the literature, although there's unpublished work of Barinkin on it. And he's given some talks about it if you want to look those up. But luckily, I don't need kind of the full strength of the results on this subject. I believe there's also some work of Hermann Stefanich also on an alternative picture of this two category. But luckily, I don't need the full strength of that subject here because I'm working in a very simple example. So let me tell you what this is. Let me put it this way. So let me first say, so if LX check were just the zero section, C mod C star, then this would be, then this two category would be modules over the category of coherent sheaves on C mod C star. Right, I have some monoidal category here and I can take its modules. The extra thing here is now that I've included this extra piece of my Lagrangian, that's not just the zero section, it's the conormal to zero. That's telling me that I also need to allow something else. So however, for us, we're going to set Y equal to, let me call it Y check, equal to the zero section, disjoint union 0 mod C star. So this is a disjoint union. I'm taking just these two different varieties, C mod C star and 0 mod C star, and this thing has a map to X check, right? Which is it has a map to C mod C star, right? Which the map is this guy goes to C mod C star and this guy goes to 0 mod C star. The answer in this case is that B3 of LX check is going to be equal to coherent sheaves on the fiber product of Y, modules over coherent sheaves on the fiber product of Y over itself. We just call it Y over. Modules on the fiber product of Y with itself over C mod C star. So we can see that if I take the first component of this fiber product, so this is going to be like a 2x2 matrix. So it's going to be coherent sheaves on some matrix modules. And this matrix is like the first part of the fiber product is C mod C star, fiber product of itself over C mod C star. The second part is C mod C star, fiber product over C mod C star with 0 mod C star. The third part is 0 mod C star, fiber product over C mod C star with C mod C star. And the fourth product is 0 mod C star, fiber product over C mod C star with 0 mod C star. So I have this 2x2 matrix of my sort of convolution variety. These are the four pieces I get from taking these fiber products of this disjoint union, and I want to take coherent sheaves on all of them and I have this, I have functors between them, so that gives me a convolution structure. I mean, yeah, I have a, sorry, I mean, it's a matrix object. And I want to take module categories for this matrix object of categories. And this is actually not so bad. I mean, this one is just C mod C star. This one is just 0 mod C star. So, right, because C mod C star, fiber product of itself over C mod C star is just C mod C star. Similarly, I can get rid of the C mod C star here. This is coherent sheaves on 0 mod on C mod C star, on 0 mod C star. This is coherent sheaves on 0 mod C star. And this is coherent sheaves on, well, on this fiber product, which I'm going to do a little trick, which, okay, I don't have time to explain, but you can do a causal duality to rearrange this to get perfect complexes on a copy of a two-shifted copy of C, which is kind of the cotangent thing here. C shifted by 2 mod C star. So I'm not going to explain that computation, but if you try to calculate coherent sheaves on this thing, then you'll get this. That's my class. Oops. So okay. So hopefully this isn't getting too difficult, but I'm about to compute this in a much more straightforward way, which is what are coherent sheaves on C mod C star? This is something which occurs often in geometry under the name of Riesz construction, right? The Riesz construction says that a filtered vector space is the same thing as a coherent sheaf on C mod C star. Filtered vector spaces. So this is, I think, something people are familiar with. If it's not, you can kind of work it out. This category has another description as modules over the A infinity quiver. So it is a quiver with sort of infinite number of vertices and arrows pointing like this, and kind of where these are the whatever piece of the filtration, you know. So kind of all of these arrows are inclusions. Then you get a usual filtered vector space, but kind of if you pass to the derived category, the DG category of filtered vector spaces, it's the same as the DG category of all modules over this quiver. So therefore, my category B3 of X is equal to B3 of X check is equal to, what's it equal to? Filtered vector spaces, built vect, graded vector spaces, right? This is just coherent sheaves on BC star. It's just C star representations, filtered vector spaces. I mean, graded vector spaces, and this one is filtered vector spaces. I know there's a shift by 2 here that I wrote down. You can't even see it anymore, but you can cancel it out by a shearing, by this sort of shearing trick. If you're familiar with the kind of shearing, if you have a graded thing, then you can use the grading to shift the homological degree. I'm not going to get into it now. This is our answer now. So now my claim is that this is the same thing as the 2 category of spherical functors. So the theorem is that module categories for this matrix of categories is equal to this spherical functors 2 category. And sort of why is that true? Let me state once again the main theorem of my talk, the one I put on the board at the very beginning. So I have a spherical functor. So okay, I have this 2 category of spherical functors. Inside this 2 category of spherical functors, I'm going to write down a Hom category, right? If I take 2 objects of this 2 category, I get a 1 category. So one of my objects is going to be my favorite spherical functor, which is a functor from filtered vector spaces to graded vector spaces. And this functor is called pass to the associated grade. That's the functor which is appearing in this matrix. And it has a right metric, which is trivial up to a shift. Suppose I plug in any spherical functor in the right-hand side. The theorem, our theorem, is that this object co-represents the functor of testing what's the left-hand category. So this Hom is actually equal to just C itself. So that's the sense in which this is the universal spherical functor. Homs out of this thing inside of spherical functors just pick you out this first category. And a way to think about that is this is sort of this category is equipped with sort of the free spherical functor. And it's like the universal thing as a spherical functor. So if you think to yourself, what's the kind of, how would I, so here's how the proof of this theorem goes, with which I might just kind of say out loud. But suppose I thought to myself, what's kind of the universal spherical functor? How would I try and build like so how would I try and build the free spherical functor? Well, I need an object on an object in C. So I need a category C. It has to have an object, right? And then it has to have, it has this, my category has this invertible endofunctor, right? So clearly it has to have also from an object X, let me call it X, it also has to have Tx, T squared X, T cubed X, T inverse X, T minus 2X, and so forth. So maybe I'll just say this. Filtered vector spaces is the is the free category on a co-augmented endomorphism of the unit. Well, let me put it this way: is filtered vector spaces. Let me just put it this way: as an object X, which X for me is going to be the trivial thing, which is the representation. So X is in this picture just equal to 0, 0, C in degree 0, 0, 0 is elsewhere. So it's kind of the simplest object inside this category. Has an object X, and it also has Tx, T squared X, T cubed X, and so forth, and also T minus 1X, and so forth, right? Where T is just going to be my thing that shifts me over forwards or backwards in here. And it has a map from X to Tx. Right?
NG, I think X, you want to have C's in all positive spots.
Yeah, that's actually correct. Sorry. Thank you. Yeah, I should have. Sorry, I didn't plan this part out. But yes, this is the filtered vector space that is just a one-dimensional filtered vector space, sort of where the filtration changes only in degree 0. So the associated graded of this vector space is just C in graded 0. So this is the way I would write that vector space. Yeah, sorry. And then now this thing makes sense. If I shift this guy over by 1, I have this map from the degree 1 shift to X. And now I'm not sure whether, okay, in the interest of not getting all my shifts and things right, maybe I shouldn't try and write this all down, but I'll leave it to you as an exercise to think about kind of why kind of if you start with a category which has an automorphism T, and also it has a map. I guess the way I've written it, it has a map from T to 1. Humbly, I wanted it to be a map from Tx to X. Then, yes, that's right. This is kind of the free category that you can do that with. Okay, so I had some other topics, but it looks like I'm out of time, so I'll just restate as a corollary. Or I guess I stated it here, kind of. So a corollary of this theorem here is that you can also recover D by passing the Fourier transform, which is the functor from graded vector spaces to filtered vector spaces. And then this 2 category is generated by that pair of spherical functors. And if you compute their endomorphisms, you get this matrix. So this is just the usual thing in geometric representation theory, whatever. You know, we look at perverse sheaves, we take some projective generators, and then we take the endomorphism algebra of that projective generator, we get some matrix, and then our category is modules over that matrix. So this is just that, but categorified. So now I did manage to state our main theorem, so I think I can, my talk goes to now, right? I have 5 more minutes?
If you want them, yeah.
Okay, well, let me pause for questions anyway, and then I can say something more.
Because it started a bit late, but you can use them or not, whatever.
Okay, well, are there any questions about what I've said so far?
Well, so yeah, I have a question. So the adjoint to this associated graded functor is, I mean, is it just take the stupid filtration?
Yes, yeah, it's just the trivial filtration.
How so the okay. And you're saying it's an exercise to show that this is spherical, or like,
Yes.
Is this cone? I mean, I assume that the whole point is that this cone is the shift functor in the end.
Yes, yeah, because so let me erase something here and write it down. So if actually, I'm gonna leave that as an exercise. Yes.
Mm-hmm.
Yeah, that's you can check that.
Okay. Cool.
Okay, I have one question. So, so is it possible to think of this using the repetitive category, where you equip a Lagrangian brain with some?
That's how I would like to think about it. So this object you should think of. So I have this Lagrangian here, and
co-cord to the zero section.
This spherical functor is a linking disk or a co-cord to this component of my
Right. So what do you equip that co-cord with? Do you equip it with a category of vect?
Yeah, that's how you should think about it. But that's just kind of a way to think about it. I mean, it's a bit ad hoc at the moment.
Right. So I wonder if you can.
But yes, that's my claim is that you equip that co-cord with the category vectors.
Okay, cool.
Okay, so let me just really quickly say one. Let me just go to the backboard now, since I have the last minute of my talk, and say one kind of corollary. So one corollary of this lemma, this Betty geometric Langlands thing I stated before, is that you can sort of ungauge, you can move the quotient by C star from one side to the other side. So we can also get that we take our A3 of L C1 C star now, and that's equal to B3 of L C. So we can switch the roles of the two spaces in our equivalence, the C and C1 C star. And in fact, we can also do this with an n-dimensional thing, and then we get this A3 of L C to the n1 C star. We can do it for a subtorus now, so C to the n mod T. And unfortunately, I've lost my exact sequence, but C to the n mod T and B3 of L for C to the n mod the dual copy of G, which these are kind of these Gale dual things. And then it turns out that also if you pick a character of T, then you can use that to specify a stability condition for this, if I take T star of C to the n and take this quotient by T, I can use a character of T as a stability condition. So let me call this character alpha. So now I can replace this sort of Artin stack with a more reasonable hypertoric variety. And if I pick a co-character of G, there's a residual G action on here. And if I pick a co-character on G, that picks me out some components in this resulting Lagrangian, which is now more complicated because it's a big product of this guy. And so this picks me out kind of a category O. Category O, it's picking me kind of a direction that picks me out like some singular support condition inside of here. So this picks me out this kind of category O sub-Lagrangian of L. And you can see that these are symmetric to this co-character. So I'll call this sub-Lagrangian L beta. And you can see that this alpha and beta are symmetric. A character of T is a co-character of T check, and a co-character of G is a character of G check. So therefore, you can use this to use a sort of equivalence of categories between A3 of the sort of category O core, I'll just call this L beta alpha, and B3 of L alpha beta. These are the kind of category O cores of Gale dual hypertoric varieties. So I've now connected the results of this talk to something that, going back to, I would say, the foundational paper in this subject is Braden, McConnell, Proudfoot, and Webster, and there's work of Ben Webster and many others building on that about proving these sort of causal duality theorems for these 3D mirror varieties. And so that we find that statement, those causal duality statements, should be recovered from this by passing decay theory. It's a kind of decategorical. So I'll end my talk there.
Any further questions?
You're getting some applause from the Zoom as well, just so you know. Yeah, yeah.
All right, then let's thank Ben again for the group talk.